Okay, so I am in Statistical Rethinking, Volume 2, Chapter 11, and we're in the medium questions. We're 11M6. So the question is highlighted here. So state the constraints for which binomial and Poisson distributions have maximum entropy. Are the constraints different for all binomial and Poisson? Why or why not? Okay. So I thought it might be a little bit interesting to discuss how maximum entropy distributions can be derived through the method of maximum entropy. This will just be a very cursory overview, and some of this material was covered in Chapter 10, but really just on a heuristic level or demonstrational level, omitting basically all of the math, and that's fine. You really don't need to know the math, but the math is interesting, and it's something that I'm trying to learn and understand better. And so I thought that I would go through this, and then in addition to this, I will be making a few videos, some playlist on the method of maximum entropy, where I'll go into more depth about these things. But we can kind of get our treads on the track here. So, so the basic idea behind maximum entropy is to maximize the quantity of entropy, right, which is a measurement of our uncertainty. And this was discussed in Chapter 10. And subject to some set of constraints. And these constraints are a little bit fluid, but they generally take this form right here, okay? That the expectation of some function of x equals some value. Okay, I know that is very, very vague, unfortunately, but we'll get through some examples here. Now, this can be written out more explicitly for a continuous variable like this. So that the value of the function at x multiplied by the probability of that value of x, and we sum over all x's, okay, or by to some bounds depending on between bounds a and b, and often these bounds are the data set or whatever. And then in the continuous case, we would obviously use the integral. Oh, that should not be pxi. That integral is a little bit messy. Let me clean that up. Okay, so we're back on track here. Okay, so now, so like I said, the exact constraints that you impose will depend on your data. So every constraint will be something you can assume or measure about your data. Okay, so we'll go through a couple of these, but one that you can always assume, because it's just simply part of the definition of probability, is that the sum of all possible values of your random variable, x in this case, equal 1, right? This is just a definition of probability. The total probability always sums to 1, right? So in the continuous case, it would look like this, and in the discrete case, it would look like this, okay? Now, we can, depending on our data, we might rewrite these, right? So, for instance, if we know that we have a non-negative variable, right, which is the case for binomial and Poisson distributions, instead of bounding it at negative infinity and infinity, we might write it from 0 to infinity or something. Okay. All right. So that's always constraint 1. We always have this constraint. Okay. So for a binomial distribution, it might look like this, right? So we might have x equals 0 to 1 of the probability of x. Okay. And the sum of all probabilities add to 1. And for the Poisson, we have a minimum value of 0, and in theory, it can go all the way up to infinity. But it doesn't matter what the upper bound is, because we always know that, again, the sum of all of the probabilities always equals 1. Okay. And you know what those should be? Yeah, that's fine. Okay. Another constraint that is common, but not strictly necessary, or if you have the following constraint, then you will be limited to certain types of distributions, okay? But that is, I'm just calling it C2 here, but there's no reason that it has to be there, or, well, if it's something that you can assume about your data, it should be there. But that this expression yields the arithmetic mean of your data, right? And so this is just the expression for the arithmetic mean. It's the value of x times the probability of it occurring, summed over all values of x. Okay. So again, that's just the definition of an arithmetic mean. Okay. Now for the binomial distribution, x bar is NP, and Poisson, we usually call it the parameter lambda. And well, as n gets really, really large, so as we have a lot of samples, lambda tend towards in P. So so the binomial and the Poisson are very closely related, right? But nevertheless, now from this point, this is where the math can become a little bit tedious and even difficult. There's some skills that you need, and so I'll just kind of sketch how this gets solved. Okay, so our term for entropy, right, which we saw up here, and our term and our constraints. Okay, so here was one of our constraints, right? That is C1, but we've just subtracted 1 over. Okay, so we've got this. And here's our second constraint. Okay, but again, I've just subtracted x bar over. Those terms, again, entropy and our constraints, they get packaged into this expression that's called the Lagrangian, or it's this kind of fancy L here. And so what this is, so it's entropy and our constraints, and then each constraint is multiplied by what is called a Lagrangian multiplier. Okay, and so so if you want to learn more about that, I've included a link right here to a Khan Academy playlist that's very good. That will kind of give you a sense about how to solve these things. And in the other playlist that I will complete at some point, I will go through solving many of these things. But the idea is that we take the derivative of the Lagrangian with respect to every probability, okay? Every p of xi, right? So again, we have the partial derivative, we have every partial derivative, so of every data point, of the Lagrangian, which means the partial derivative of hypertrophy with respect to every probability, the partial derivative of each of these kind of constraint-looking things with respect to every probability. Okay. Now when you do that, the derivative for h, for entropy, one of the terms in that derivative happens to be the probability of xi. Okay, so the answer, or well, the solution then to every derivative or every partial derivative of the Lagrangian includes p of xi, and then we go about, because it's in the expression, we just go about solving for p of xi, and we get a generic expression for p of xi, and that becomes our probability distribution. Okay, and along the way you can solve for the Lagrangian multipliers. You don't always need to. Sometimes you need to, but anyway. So once we've done that, then we have completely delineated the probability distribution. Okay, and it just so happens that when you have the set of constraints that we've detailed here, you get the binomial and you get the Poisson. Okay, so so anyway, I just thought it might be a little bit interesting to get a little bit of a deeper take on some of this stuff. And I guess we'll call it good there.